Sanjay, do we begin soon or how do we do it?
Sure, so I think I can start by directly playing the video of our sponsors. I hope that's fine.
So I think that should be okay. But do you want to wait for? I think we waited 2 minutes. So I guess yeah, sure.
Yeah, we can get started. Sir.
Yes. Okay. Go ahead. Yeah, I think you can share the video first. Yeah.
India, a nation powered by 1 billion dreams. Dreams that we aspire to fulfill every day. Together with our collaboration and commitment, as India embraces to be a $5 trillion economy by 2025, we are all geared up to be a part of this monumental journey to usher in a brighter, better future. Together, we touch ordinary lives and make that difference. We better every day. Together, we make steel that you carve into your agri-equipment. Together, we sow the seeds of success. We make steel that gives the grit and grind to your heavy equipment. Together, we change the landscape of our country. We make steel that you beautifully mold into your automobiles, just to drive our nation on its path towards prosperity. We make steel that you transform into solar energy. Together, we steer our nation towards a greener tomorrow. We make steel that relays your transmission lines, just to brighten the future of millions. We make steel that styles your appliances. Together, we bring happy smiles. We make steel that adorns your development projects. Together, we provide shelter to millions. We touch lives, make them better together, every day. We empower communities, make them better together, every day. We nurture dreams, make them better together every day. As India embarks on its accelerated growth journey, we are firmly placed to leave our mark in it. Together, we touch millions of lives and make them better every day.
All right. So welcome to all.
I'm sorry, sir. There's another video. I guess.
Sorry. Yes, go for it then.
रामू, सुना है कि तुम्हारे खेत में अच्छी फसल हुई है?
हाँ, काफी अच्छी फसल कटी है भैया इस बार। जब मुझे पता चला कि मेरे खेत में समस्या है, तो खेती विशेषज्ञ की सलाह पर मैंने सरदार खाद का इस्तेमाल किया। अब देखो नतीजा।
क्या बात है, मैंने तो बहुत कोशिश की, लेकिन नतीजा खराब ही निकला।
हर फसल की अपनी जरूरतें होती है और हर खेत की मिट्टी अलग है। इन सब के लिए GSFC ने विभिन्न प्रकार के खाद सरदार ब्रांड में पेश किए हैं। तुम सीधे उनके टोल फ्री नंबर पर फोन करो और अपनी समस्या का समाधान पाओ, और फिर अपने निकट के GATL किसान सुविधा केंद्र में जाकर उपयुक्त खाद वाजिब दाम में पाओ। सरदार, खेतों की जान, किसानों की शान।
All right, Sanjay, shall we begin?
Yes, sir, we can get started.
Okay. Hello, all. Good morning, good evening, wherever you're joining us from. My name is Prasanna. I'm an assistant professor at IIT Gandhinagar in the physics discipline. I just want to begin by letting you know about Amalthea, which is the annual student-run technical summit of IIT Gandhinagar, which has been running successfully for 10 years. This year marks the first online edition of Amalthea, and the webinars are an important part of this year's Amalthea. And today is the fourth webinar of this series. And it's my pleasure to welcome the speaker for today's webinar, Professor William D. Oliver, who is jointly appointed as an associate professor of electrical engineering and computer science, and also as the Lincoln Laboratory Fellow at the Massachusetts Institute of Technology. He serves as the director of the Center for Quantum Engineering and also as the associate director of the Research Laboratory of Electronics. Professor Oliver's research interests include materials growth, fabrication, design, and measurement of superconducting qubits, as well as the development of cryogenic packaging and control electronics. He is a fellow of the American Physical Society, senior member of the IEEE, serves on the US Committee for Superconducting Electronics, and is an IEEE Applied Superconducting Conference board member. He received his PhD in electrical engineering from Stanford in 2003. Today, he'll tell us about the very topical and highly interesting field of superconducting qubits. His talk is titled Quantum Engineering of Superconducting Qubits. Please keep your questions coming through the talk, and if there are some pertinent ones, William has kindly agreed to take them during the talk. I'll try and pitch them during the talk. If not, we'll take as many questions as we can towards the end of the talk. All right, over to you, William.
Okay, thank you very much for that kind introduction, Prasanna, and it's really my honor and a pleasure to be here today to talk with you about superconducting qubits in general, and then also some of our research as well. Let me just confirm with the organizers that this is coming through on the screen properly.
Right, yeah, it is.
Okay, great, thank you very much. Yeah, so my name's Will Oliver, and I work at MIT, as you just heard. And this talk is really geared towards students today, and I hope that we can have a good conversation. If there's a question during the talk that's really urgent to help to understand, maybe I'm not communicating well, please feel free to answer it, and then otherwise we'll answer questions towards the end. So by way of introduction, you know, quantum information science and technology spans a wide range. There's quantum sensing, quantum networks, quantum computing. And if I had to give an engineer's definition to this, I would say that quantum information science utilizes a quantum mechanical description of nature to sense, communicate, and then process information in ways that are unobtainable or certainly practically prohibitive by a means of a classical description of nature. And today we're going to talk primarily about quantum computing. But before we get into that, maybe it's worthwhile to go back and look at the last century of classical electronic computing. Now, the vacuum tube, as you know, the triode vacuum tube was invented in 1906. And it was used for radio transceivers for decades before it found its first use in a computer called ENIAC, developed at the University of Pennsylvania in 1946. And of course, it was a very large computer, but not very powerful. You can see this is a man standing here by a room full of what constitutes ENIAC. Now, just a year later, the first transistor was invented at Bell Laboratories. And although maybe 10 years later, we had a fully transistor-based classical computer called TIXO, or TX0, in 1956, and that was developed here at MIT. It didn't look anything like the processors that we have today. These transistors were soldered together, and it used a magnetic core memory. So very different than the integrated circuits we know of. That would be developed in the late 50s, and originally on germanium, and then the next year on silicon. But it would be another 20 years to take us into the 70s when we first saw the what I would call the first real integrated circuits. Here's the Intel 4004 in the early 70s, had 2,000 transistors, followed shortly by the 8008. That's a 4-bit and an 8-bit processor. It would be another 20, 25 years to get into the 90s, and we start seeing millions of transistors, for example, the Pentium Pro, and then another 20, 25 years to get to where we are today, which is that we have multi-core processors and graphical processing units with billions and billions of transistors. So looking back at this history, it's well over 100 years of development to get from the first vacuum tube logic element to the multi-core billions of transistor processors that we have today. So well over 100 years of development. We can compare with that quantum computing, which is much more nascent. In the early 80s, people like Richard Feynman, shown here, but also Uli Mannin and others, suggested that if you want to simulate a quantum system, you should use a quantum system to do it, because it's not so easy. There's lots of degrees of freedom, and a classical computer will quickly become overwhelmed. Now, people thought about, okay, how do I make a quantum algorithm? What does that even mean? And we started to see the first answers 15 years later, in the mid-90s, when people like Peter Shor, Lev Grover, Eddie Farhi, Nishimori in Japan started making the first algorithms, such as Shor's algorithm for factoring large numbers into its constituent primes. And this really launched the field of quantum computing, because these are very important problems. And if we could efficiently break RSA encryption using Shor's algorithm, that would be a big deal. Now, around that time, Peter and colleagues, Steen and others, developed the error correcting codes, the first error correcting codes that apply to quantum computers at a theory level. And then we fast forward another 20 years to get to where we are today, which is that we have the first small scale processors available in the cloud, 50-ish qubits, and a first demonstration of quantum advantage by Google in the fall of 2019, so about a year ago. So what's the takeaway message here? Well, the first is that quantum computing is real. It is transitioning from scientific laboratory curiosity to a technical reality. But we know that advancing from discovery to useful machines takes time, and it takes engineering. And of course, it takes physics and science all through many decades to make this a reality. The other takeaway might be that you have to be in the game to play. And what I mean by that is many of the companies that take advantage of classical technologies today were in it for a long time, some of them even from the very beginning. And so I believe quantum will be similar in that the companies and the places that will take advantage of this technology in the future are the ones who are working in it and developing it today, rather than waiting for some ultimate result to occur. Okay, and so with that as my basic introduction, let me talk about quantum computing and what it is. We'll then talk about superconducting qubits in particular. I'll talk about one example of engineering a quantum system, designing filters to improve coherence times and mitigate errors. And then we'll talk about 3D integration primarily, just a high-level view. So how is a quantum computer different? Well, we know that classical computers are based on classical bits of information, for example, the voltage on a transistor, and they take states 0 or 1. It's in one state or the other. The error rates are very low. For our computers we're using today, it's better than 1 part in 10 to the 20. And so these are basically discrete states that are almost perfect. And their measurement is deterministic. If you set it in state 1, you'll measure a state 1. Set it in state 0, you measure state 0. Now, quantum computers are different. They're based on quantum versions of these bits, which basically, from a physics standpoint, can be any coherent two-level system. We represent this on the Bloch sphere, which you can think of as the planet Earth. And the North Pole we'll call state 0, and the South Pole we'll call state 1. And if you live at the North or South Pole, you're basically a classical bit. But if you live anywhere else on the surface of the Earth, you're in a superposition of 0 and 1, weighted by these factors alpha and beta. And importantly, what we want to remember is that this is a single state. So there's one vector pointing somewhere on the Earth, and so it's one state. It's not two states, it's one state. And the one state carries aspects of both 0 and 1 simultaneously. We can write it in a linear algebra notation like this. And the important feature here is that these are quantum mechanical superposition states where measurement is probabilistic. So for example, if we put this vector on the equator and we make a measurement, half of the time we're going to get 0, and half of the time we're going to get 1. And even if we identically prepare this qubit on the equator in the same place, each time we make a measurement, probabilistically, we're going to get 0 or 1. And so what this means is quantum computers rely on encoding and, in fact, measuring information in fundamentally different ways. Of course, and this has implications for how they behave inside a real computer. Now, on a classical computer, if you have n bits, you can form one n-bit state. And there are exponentially large number of them, 2 to the n. For example, if n equals 3, then we have 8 different states from 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. But what's important is that we can only represent one of them at a time. So for example, let's say we represent 0, 0, 0, and we put it into our computer, classical computer. It will calculate some function of 0, 0, 0 and put it at the output. If we want to see the answer for a different input, we have basically 2 choices. One is we can parallelize the hardware, make many copies of the hardware, and put in, simultaneously different inputs and get different outputs. Or we can take one of these computers and sequentially in time put in a different input and get a different output. But either way, there's an exponentially large number of these different states, and so it will take either exponential space or exponential time. Now with a quantum computer, these qubits can, again, there are 2 to the n different, what we'll call components, but you can put all of these components into a single superposition state at once. And so you can write a large superposition state with all 8 components, each weighted by a factor, alpha, beta through gamma. And what this leads to is a quantum mechanical version of parallelism, and importantly, quantum interference. So conceptually, we can think of taking a large input state, which is a large superposition state, put it into the computer, and it will calculate on that and give out new coefficients for each of these at the output. We'll talk about how that becomes an algorithm in a moment. But that's basically the difference, this quantum version of parallelism and interference. Now, when we operate a quantum computer, we operate it with gates, and it's quite analogous to how we operate classical computers. Classical computers, of course, rely on Boolean logic and Boolean gates, such as the single bit NOT gate, AND gate, OR gate, etc. And there's a whole handful of these. And the important thing is that with just a small number of them even, not even this whole list, for example, the NOT gate and the AND gate together, you create what's known as a universal gate set, which means one with just these 2 gates can perform any Boolean logic algorithm. And the other thing is it's not unique. There are other combinations of gates that you can put together to create a universal set. Now, quantum computers similarly run on a small set of single qubit gates, which I won't read through them all here, but they perform rotations around different axes of the block sphere by a prescribed angle. I'll show an example in a moment. But there's a handful of these single qubit and also 2 qubit gates where the operation on, say, qubit 1 depends on the state of qubit 2, and so we call it a conditional gate. But with just this small handful, and even a subset of them, we can form what's called a universal set of quantum gates, which allows us to perform any quantum logic algorithm. Now, in fact, it can also perform any Boolean logic or classical algorithm as well, but it's important to remember that it often does so no better, and in many cases worse, than a classical computer. But for a small and growing number of quantum algorithms, the performance vastly is improved over classical algorithms. So let's take a look at what these gates look like, and we'll look at the quantum computing analog of a classical NOT gate. As you know, a NOT gate will take Boolean 0 and turn it to 1, or 1 and turn it to 0. And the quantum version of this NOT gate is called, for example, an X gate. Now, an X gate will also take an input 0 and turn it to 1, and vice versa. And we can see that in this simulation here. Now, I realize the video may be a little bit choppy, but I hope that you can see the salient feature, which is that this vector pointing at the North Pole 0 is rotated to the South Pole 1 by applying a pulse whose envelope is shown here in red. Okay, and then this red arrow coming in and out of the screen is basically representing that envelope. Now it's called an X gate because we're rotating around what I'm calling the X-axis here. And in fact, it's called a pi pulse because the rotation angle is pi, 180 degrees. Now the way that I've shown it here, this is just a classical gate. It took a classical state at the North Pole and took it down to the South Pole. But the feature here is that the starting point can be anywhere, and now it's a manifestly quantum gate, rotating again 180 degrees from some arbitrary starting point to some final state. And in fact, what this gate is doing is taking a superposition alpha 0 plus beta 1, and it's swapping the alpha and the beta weighting on the 0 and the 1. These prefactors are coefficients. So this is a quantum gate that works on any state starting at any point on the Bloch sphere or the planet Earth. We can now take an example of a 2-qubit gate, and the one that I'd like to compare against is classical XOR gate. Now, the XOR, or exclusive OR, as you remember, has two inputs, X and Y. These are 2 bits. And one is called the control bit, and the other is called the target bit. And if you look at the truth table here, the input, when the control bit is 0, when X is 0, the target bit Y is just passed through and is unchanged. But when the control bit is 1, we flip the target bit from 0 to 1 or 1 to 0. So this is called a controlled NOT gate or a conditional gate, where the operation on this bit Y depends on the state of the bit X. Now, the quantum version of that is called a CNOT, or controlled NOT gate. Again, you now have qubits X and Y for the control and target qubit, but otherwise, aside from writing these as quantum states, the truth table is basically the same. And what's important is that the rotation of qubit Y will depend on the state of qubit X. And we can take as a very interesting example this input state where the control bit is in a superposition of 0 and 1, and the target bit Y is just in its ground state 0. And we can take what happens when we can perform a controlled NOT gate on these 2 bits, qubits. So for the portion that's 0 on the control, we leave Y, the target, the same. But for the portion of the superposition where the control bit is in state 1, we flip the target bit to 1. And now what we see is what used to be a separable state in terms of an X component crossed a Y component. Now we can no longer do that. And when we can no longer write a state in this way, it's called an entangled state. It's a special type of superposition state, and it can't be factored into an X-like and a Y-like component. And in fact, that's true no matter what basis you look in. So again, these are just 2 examples of the types of gates that form a universal gate set for quantum computing and allows us to run any quantum algorithm. Now, what these algorithms look like is what I'm trying to illustrate here graphically. We have an algorithm and we have an input state, and generally the input state is going to be an equal superposition state. So all components in the superposition state with equal weighting factor in front. And we feed this into our algorithm, which prescribes some single and 2 qubit gates. And so the single qubit operation gets applied to one of the qubits. But what's important is that it impacts all components in the superposition state, all 2 to the n. So 1 qubit, 1 pulse, but we're actually performing a rotation across the entire space. Now that's followed by quantum interference, which between these 2 will change the value of the coefficients in front of these, the weighting of each of these. We'll also sometimes apply coupled qubit operations, whereas we just saw the state of one of the qubits rotates or affects the other qubit. And that's followed by quantum interference. And this proceeds according to a prescription which constitutes the algorithm. And the goal of any algorithm designer is such that at the end of the day, one of these weighting factors is going to be unity or very close to unity. And that's because when we make a measurement, we basically have an exponential collapse or slowdown, if you want to think of it that way, where the measurement that we achieve is probabilistic, but it goes as a probability of the magnitude squared of this coefficient. And so if the coefficient's close to 1, then with probability almost 1, we're going to measure this output, and the algorithm designer has encoded the problem in such a way that this is the answer to the problem, right? Now, if this didn't happen, we would randomly get some output that would go as the magnitude squared of these coefficients, and we would have to run it many, many times, in fact, an exponential number of times, and it wouldn't be efficient. So that's the trick with writing an algorithm quantum mechanically, is you want to make sure that your output weighting is basically on one or just a very small number of these output states, so that when we measure with high probability, we get the answer that we're looking for. Okay, now there are many quantum algorithms that exist today, and more are being found. I won't read through this whole slide, but let me just highlight the algorithm, the classical time, and the quantum time. And you can see for most of these, it's an exponential or polynomial speed up. So quantum simulation, quantum chemistry, quantum materials, Shor's algorithm for factoring, but there are other number theoretic type algorithms. Sampling solutions to linear systems of equations where the size of the matrix is very, very large. Optimization problems, and also search, Grover's algorithm. Now, some of these, we don't know the speed up. For example, optimization, it's hard to quantify the speed up. And of course, all of these have limitations which are still being researched today. So this isn't over, but there's a lot of work going on to make these algorithms better and to find new algorithms that we can run on the quantum computers that we have today or will have in the near future. So you could ask, okay, why don't we just build a bigger quantum computer right now? And it's related to two time scales. One is the coherence time of the qubits, and this is the qubit's quantum mechanical lifetime. If we have a qubit state, we know at, say, time t equals 0 exactly what state we put it in. But it's always interacting with its environment, and we don't have control over that. And so over time, the state is decaying and eventually lost. Now, it's important to remember the qubit didn't disappear, the qubit's still there, but the state that it is in becomes unknown to me due to the interaction with the environment. It's not where I would predict it to be based on the solution to the dynamical equation of motion known as Schrödinger's equation. Okay. Now, the gate time is the other time scale we care about. And that's the time to perform one of these qubit gate operations, whether it's a single gate or a couple qubit gate. It's just the typical time that it requires to do that. And of course, the figure of merit is how many gates can I apply within the qubit's coherence time that I have. And of course, more gates per lifetime is better. It's important to note that long coherence times are good if you fix the gate time, but it's not enough to just say that I have a long coherence time qubit, because the gate time is also important. So one, maybe ridiculous example is a neutrino. A neutrino, we know, is very, very hard to measure. It's very, very hard to control. So even though it may have almost an infinite lifetime, it's useless as a qubit because the time it would take to implement a gate, if we could do it at all, is also probably very, very long. Okay, so we can use this metric to compare different qubit modalities against one another. And what's listed on this axis are the operations before an error, which is basically one-to-one in something we call the gate fidelity. So if I have one error out of 100 gates, then basically I have 99% gate fidelity, and so on. Now, 99% is not a magic number, but an important number, because this is the most, roughly speaking, it's the most lenient value or threshold required for quantum error correction. You want to be above this number as much as possible. And quantum error correction, basically, in a nutshell, is by adding more qubits and redundancy, we can make the overall system perform better. And we have classical error correction as well. But as you might imagine, if the individual components are too faulty, then adding more of them doesn't help, makes it worse. And it's only when you make them better than some threshold that the situation becomes improved. And that threshold, again, for the most lenient error correcting codes is around 99%. And of course, on this horizontal axis is gate speed, and so the upper right corner is the best performance. Now, there are a number of modalities that have solidly demonstrated single qubit gates. Many of these are now demonstrating 2 qubit gates. And then there are a number of modalities that have demonstrated what I would call a universal set. And some of these are including trapped ions, superconducting qubits, silicon quantum dots, NV centers, and neutral atoms. Now, the two leading candidates today, I would say, one is trapped ions, and I just list here a few colleagues of mine at MIT who are working on this, and superconducting qubits, which is my own area of research along with my colleagues at MIT. And if I had to say what we're researching, of course, for trapped ions, they're trying to make their gates faster, and they're also trying to make a better 2-qubit gate performance. For superconducting qubits, we're already, I would say, fast enough, but we want to make our gates better. We want to make the fidelities higher. Now, in terms of NV centers and neutral atoms, here are some colleagues we have at MIT working on these technologies. And I should say NV centers also, in addition to being a computing modality, they perhaps more strongly are a quantum sensing modality. But anyways, the point is that, look, there are many candidates here to develop or realize a quantum computer, and the ones that are leading today may not be the ones that lead in the future. Just as we used to have vacuum tubes, then we had bipolar junction transistors, now we have CMOS. Technologies change over time. Okay, and so with that, let me now transition to superconducting qubits. So how do you build a superconducting qubit? It's basically an LC harmonic oscillator, an LC circuit, resonance circuit. And if you cool this resonance circuit down to a low temperature, where low temperature means that the energy scale, Boltzmann's constant K times temperature T, KT, is much smaller than Planck's constant times this resonance frequency of this circuit. If you go into that regime, you will have a quantum circuit. It will have a parabolic potential because it's a harmonic oscillator, and the energy levels will be equally spaced, as it should be for a harmonic oscillator. Now, these levels will be well resolved, so it is quantum mechanical, but it's not useful as a qubit because the 0-1 transition frequency is no different than the 1-2 and the 2-3. All right, so we can't isolate the bit of information. So the way we get around that is by introducing some nonlinearity to make the oscillator anharmonic. And the way we do that is by introducing a Josephson junction, which is a superconducting device where it has two superconducting leads separated by a thin insulating barrier. And one of its properties is that the current going through the junction changes the inductance. Or said another way, the inductance is nonlinear in the current that travels through it. And so by replacing our inductor with this nonlinear one, a Josephson junction, it changes the potential profile. In this case, it's a simple case, but it changes it to a cosine rather than a parabolon. And a cosine, if you look at the energy levels in this well, they're no longer degenerate. And because of that, we can basically isolate 0-1, put a box around it and say, that's my qubit. And it's off resonance from the other transitions. Okay, that's a property called anharmonicity, the degree to which that is true. Now, this is called a fixed frequency transmon, and it's one of a Mendeleev table full of artificial atoms that we can make out of superconducting circuitry. Now, we could take this junction and open it up into a loop, and by threading a magnetic field through this loop, called a squid loop, we can make the qubit's energy levels tunable. We can add a shunt capacitor, which can stabilize the qubit in some way. We could add more junctions, which looks like a larger inductance. There's many things that we can do to change the properties. And when we say change things, what we're talking about is designing. These are parameters that we have, the properties of the junctions, the size of the capacitance, the number of extra junctions, or the size of the inductance. And with that, we can define or choose the qubit properties we desire, such as the qubit's frequency, whether it's tunable or not, the degree of anharmonicity, or the sensitivity of the qubit to different types of noise in the environment. We can trade off charge noise for flux noise, for example. Okay, and as a result, we have a huge number of these different types of qubit designs. Now, I mentioned that the temperature has to be cold, and the qubits, we choose them to have a frequency around 5 gigahertz because that's convenient for the control electronics we use. But that means that the temperature has to be much smaller than 250 millikelvin. And we can do that. We can use a machine called a dilution refrigerator, which can cool these samples down to 20 millikelvin or even colder. Now I'm showing a dilution refrigerator here. The diameter is about 1/2 meter. The depth there is another 1/2 meter. And everything in this 1/2 meter by 1/2 meter volume is below 20 millikelvin. Okay. And these are turnkey devices. You buy them and they generally work. And you can see many things in here like switches and coax cables, attenuators, isolators, circulators, all of which operate at these low temperatures. So this part is not, I would say, a challenge now. Maybe 30 or 40 years ago, it was the research project itself, but now we use it to do other research. Now, of course, we have to fabricate these devices, and to do that, we use silicon technology. Our wafers are silicon. We use the same tools that are used to deposit and etch materials in a silicon foundry. What I'm showing here is a 200 millimeter wafer that we fabricate on. And we zoom in on one device. Here's 5 qubits in a row. Each plus sign here is a qubit. These meanders you see in the northeast are readout resonators. If we zoom in on one of these plus signs, you can see the control lines coming in from the southwest. The plus itself is a capacitor. It's a lateral capacitor. Rather than parallel plate, we put the capacitor next to the ground. And then if we zoom in on this part here, we can see what I call the squid loop with 2 Josephson junctions. So we put a magnetic field in this loop and we can control the qubit energy level splitting. And each junction looks like this. And now we're at the 100 nanometer scale. And of course, this requires fabrication facilities. I just show a couple pictures of one that we have at MIT campus, a new one, and also one that we use out at the Lincoln Laboratory campus. Now, we control these with basically microwave gear or equipment, such as local oscillators and arbitrary waveform generators, and standard IQ mixing. And what an IQ mixer does is it takes the input in the I or the Q port and multiplies it by a continuous wave from a local oscillator. And if this, say, or I or Q is made by an arbitrary waveform generator, it's a pulse, then what comes out are pulsed microwaves, okay? And the difference between I and Q is just whether the mixer will impart a 90-degree phase shift or not onto this underlying oscillation. So I means in phase, and we'll associate that with the x-axis. Q means quadrature or 90 degrees phase shift, and we'll associate that with the y-axis. And so we can see rotations here now according to whether we input the pulse into the I or Q axis. So here red means Q, and we'll rotate around the y-axis. If it has half of the area, it only rotates half as far, so that's a pi/2 pulse to the equator, and then back to the North Pole. Now blue is going to mean an I in phase pulsing, which is around the x-axis. Of course, we can do it around the negative x-axis, and so on. And so this is how we can achieve universal control on a superconducting qubit. And I'm showing here x and y rotations, but we can also do z rotations. But with 2 of them, that's sufficient. And of course, we can look at how the qubits have improved over the years from late 90s at about a nanosecond up to today, where these qubits are now exceeding 100 microseconds and more. And this is just a remarkable improvement, orders of magnitude over the past 20 years. And it's been due to a combination of materials, fabrication, and design by groups worldwide. And if you'd like to learn more about superconducting qubits, I can represent this paper right here called The Quantum Engineer's Guide to Superconducting Qubits, which is a longer paper. And then a shorter version of just an overview is this one right here by Kjaergaard et al. And for material science, this paper at the bottom here in the MRS bulletin, it's a little bit old, but the material in there is still valid today. And so where we are now is with chips that are online. And I would say we have nascent commercial quantum processors, quantum computers from Google, IBM, Rigetti. D-Wave does a different type of quantum computing called annealing, and Intel. But I think all of these, as remarkable as this is, all right, and it is truly remarkable. I also show this picture here, which is clearly not a processor, but it's the first flight of the Wright Flyer at Kitty Hawk in the early 1900s. And this is basically the stage that we're at today. We got the plane off the ground. It can fly. there's still a long way to go before we're all boarding jet airplanes and going on vacation to other countries, right? So there's still a long way to go from where we are today to having quantum computers at scale. But it's a very exciting time. So to realize the promise of these quantum computers, we need to engineer systems that are robust, reproducible, and extensible. And I'd like to give one example of that in the next section. So if we're going to architect a quantum information processor, QIP, we need to have an architecture. And this one is due to Cody Jones. And it should look fairly familiar, comparable to, say, a classical architecture. So there's an application, a human-computer interface at the top. And at the bottom are the physical qubits, the hardware. There's a logical controller, which interprets the algorithm and decides how to implement it on the hardware that we have. But there are two layers in here which I wouldn't say are entirely new, but are certainly heavily used in a quantum computer. And those are passive error suppression and active quantum error correction. Now, in a classical computer, we sometimes do have error correction for memory, for example. But here it's embedded in part of the quantum computer right from the start. And what that means is that on every single clock cycle, we need to do this error suppression and error correction along with implementing an algorithm. And to give an idea of what this looks like, I have a few videos. And again, I hope they're not too choppy. So let me at least just show this picture right up front. I don't know if you're familiar with this sport, but it's called lacrosse. It was developed by the Native Americans in the US hundreds of years ago. And basically the idea is you hold a stick with a basket and you want to keep the ball in the basket. And you run down the field and then eventually throw it into a goal. Now, of course, there are many difficulties in doing that. And one of them, as I'm going to show here in this video, is that you are running across the ground. And of course, the ground is not smooth, so it's bumpy, and that's noise. And in addition, just you running introduces more noise. And so as this person runs across the ground, you can see that the ball is bouncing and eventually falls out. And I would say this is analogous to the physical qubits operating in their own environment if we don't do anything. Okay. Of course, that's not how you play lacrosse. The way that you do it is doing something called cradling, where you rotate your hand back and forth and in a passive way. You don't think about it. You just always do it. And so this person is illustrating that now. And by doing this, he's decoupling the noise of his running in the ground from the ball in the basket. And so the ball stays where it should stay by doing this. And he can run the whole length of the field and then eventually scores by throwing it into the goal, as shown here. Okay. So that's called passive error suppression because this player is just always doing this, not thinking about it. It's not active. Now, occasionally we have a problem. The defender will come up behind, and even though this person is cradling passive error suppression, sometimes the defender or the big D, decoherence, comes up and will knock the ball out. That we can't help. And when that happens, we have to do a few things. First, we have to recognize that an error occurred, the ball's on the ground. We then have to go over and pick up the ball actively, and then we start the passive error suppression all over again. And this is active error correction. And this is a topic that people are now just starting to demonstrate with quantum bits and superconducting qubits. What I'd like to focus on today, though, is the passive error suppression. Now, what I'm showing here is something called a Rabi oscillation. So if you drive your qubit from the north to the south pole over and over again, in the absence of any decoherence, then it should just oscillate like a sine wave for all times. But of course, it doesn't do that. It decays over time. And the reason it decays is because of decoherence. And there are a couple different timescales that we think about. One is the relaxation rate. We call that gamma 1, or maybe 1 over T1. T1 is the time scale. And that's the time it takes to relax a qubit in its excited state down to its ground state. Now, I say that because in our systems, we're so cold that we almost never excite from the ground state to the excited state. It's almost always a relaxation event. Strictly speaking, T1 goes both directions. But in our qubits, it's basically just the relaxation from the south pole to the north pole. Now, there's another decoherence mechanism that's called T2, time T2. And that's what happens to the coherence of, say, a superposition state anywhere on the Bloch sphere, but let's imagine one on the equator to be concrete. And there are two ways that things can go wrong if you're on the equator. First of all, the excited state portion of your superposition state could itself relax to the South Pole, and that's it. Now everything's in the ground state. And so T1, energy relaxation, is certainly a part of T2. But in addition, even if you stay on the equator, you could lose track of which way you're pointing, right? Which longitude am I actually pointing at, due to a process called dephasing. We lose track of the phase around the circle that we call the equator. And so T2 is a function of both energy relaxation T1 and this dephasing time T5. Now, in the absence of dephasing, T2 is limited to twice T1, it turns out. And in this qubit, we measured a T1 that was 12 microseconds, but a T2 that was 2.5 microseconds. And the fact that T2 was so small suggests that the dephasing was quite strong. This T5 was quite short. And that's a prime candidate for using error suppression techniques. Okay, so let's look at dephasing in a little more detail. So let's say we have two energy levels, 0 and 1. They're separated by a fixed energy, E01. And if we put our qubit in a superposition state, because state 1 is at a higher energy, it's going to accrue phase at a faster rate. And we can write it in this way. Now, in this form, if E, the energy separation, is fixed, then the phase accrual as a function of time is fixed by this formula. And so at any point in the future, I can tell you what the phase is. But in the presence of noise, what happens is these energy levels fluctuate, they jiggle. And so as a result, we have, of course, an average energy level separation, but then we have stochastic fluctuations about that value. And that leads to, of course, an average phase with time, but also a stochastic fluctuating portion. And that's what leads to this dephasing. Now, phase, we know, accrues in an exponent, so e to the I phi. We can take the ensemble average of that. And this phase is basically the time integral of this energy level separation, okay, divided by h bar to make it a frequency. And that's what we would calculate. Now, we can make a very reasonable assumption that there are lots of defects in my environment causing the dephasing, which due to central limit theorem will lead to Gaussian distributed noise and Gaussian distributed fluctuations, which means that when we calculate this ensemble average, we get this functional form. And it takes on a fairly intuitive form, which I'm going to describe here. So first of all, it's a Gaussian decay function. And this term here is, if I have a noise in my environment like magnetic field, let's call it lambda, how much does my change in lambda change my energy levels, right? So that's one term. And then the second term here is what is the strength of my fluctuations of the magnetic field, or lambda? And that is an integral of something called the power spectral density. So the power spectrum of the noise as a function of frequency. If I just integrate that over all frequencies, I basically get back the variance of the noise. But there's another term in here which is called the filter function. And this shapes the noise. And this filter function depends on what we do in the time domain with our pulsing. And I'm going to show some examples of that. So the first example is I don't do any pulsing in the time domain. I do, of course, set up the problem by doing a pi/2 pulse at the beginning and at the end. This is called a Ramsey interference fringe. And what you're seeing here is that the first pi/2 pulse brings me to the equator. And I'm now simulating what happens in the presence of noise. And you can see that this Bloch vector becomes completely depolarized. I can't tell which way it's pointing by the end of this experiment. Now, the noise that I'm simulating is a common noise called 1/f noise, which is shown here as 1/f as a function of frequency. And what I'm going to presume in this argument is that the noise is basically quasi-static, meaning that this experiment is short enough that most of the noise power is at a low frequency so that the energy levels are static during one experiment, but from experiment to experiment, it can change value. Okay, we call this quasi-static noise. The reason I make that assumption is that if I do, then I can look at this time tau, but while I'm running the experiment, and I can assume that my energy levels are fixed. And so this becomes basically a boxcar function. And the Fourier transform of a boxcar is in fact a sinc function, we know. And so this filter function that I told you about is basically a sinc function. And so it passes the noise at zero frequency or close to zero frequency, which for 1/f noise is terrible, right? That's where the noise is the strongest. So this is a really bad strategy. And it's the reason that this depolarization was so bad. So of course, that's not what we do. This would be the analog of the child running along the ground, but not doing any cradling, okay? The noise is dominant. But what we can do is we can cradle, and the cradling here is represented by this pi pulse. You know, maybe think of it as 180 degrees rotation. You can go back and forth. We'll see that in a minute. But by doing that, we basically invert the dynamics on the equator so that these block vectors will eventually refocus. And therefore, we see that the depolarization is greatly reduced. Now, in this language that we've been talking about, we basically put a pi pulse in the middle of the evolution. We now have two rectangle functions, one with a plus sign, one with a minus sign after the pi pulse, and its Fourier transform is now shown in green. And what we see is that it's zero at zero frequency, but it's also shifted, its centroid is shifted out to higher frequencies. And so in an integrated sense, this will pass much less noise than the case where we didn't have a pi pulse. So this is called a refocusing pulse or spin echo. It's a very simple example of noise filtering. We can, of course, add more pi pulses. So think of this as going back and forth, right? And now the Fourier transform for this evolution, these functions, is this red filter function, which is at yet an even higher frequency and a stronger cutoff at 0 hertz. So for noise that's decreasing with frequency, this is a great strategy to improve the dephasing. And you can, of course, continue and add more and more pi pulses. This, of course, has a name, Carr, Purcell, Mayboom, and Gill sequence. And as you add more and more of these, you can see that this overall decay time keeps improving up towards the twice T1 level. If you remember on the equator, if you get rid of all the dephasing, the only thing that's left is T1 relaxation back to the North Pole. Okay, so this is a very simple example, but a clear one of how we can do passive error suppression while we're running quantum algorithms. This is just done in the background passively. Now, I'll just mention that if you look at this as an engineer, you might say, wow, that's interesting. These are narrow filters. I wonder if I could use them to, in fact, sample the noise spectrum that I have in my environment. And in fact, you can do that. I won't go into detail on it, but we've published a lot of works on how you can use this feature, in fact, to learn about your environment. And that's called noise spectroscopy. And once you know what the noise spectrum is, you can then modify the spacing of these pulses to, in fact, further improve the coherence times. But I won't have time to talk about that today. But my point is that, look, concepts like filtering and pulsing in time and control are part of quantum engineering of these systems. So let me just give a few pictures now as I wrap up. I realize I'm getting out of time here. So in a gate model superconducting qubit quantum computer, I just show some pictures here again. This is a 5-qubit sample. The Ramsey time today is up at around 100 microseconds. The 1 and 2 qubit fidelities that we've demonstrated are almost, the 2 qubit fidelities are almost 3 nines. 1 qubit exceeds 3 nines. And so we're in the range where we can start thinking about active versions of error correction. The largest chip in my group anyways is a 4x4 qubit array. So 16 qubits shown here. And one thing that we're using it for is for random walks in 2 dimensions. Now, a random walk in an array like this, we have to think of it in terms of, you know, walking around a city like Manhattan, and the Manhattan distance, if you want to go from point A to point B, is not the direct green line. If we were a bird, maybe it would be, but of course we're walking in blocks, so we have to count blocks and distance in this way, like the blue line. And so in our qubit, what that means is that we can look at a distance in terms of 1, 2, 3, and then 4. And when we do that, what we create an excitation at 1, and then we look at the Manhattan distance from the origin, and we see how this excitation propagates in 2 dimensions. And we can see that it just randomly walks back and forth. It's not really random, but it's called a random walk. And this is in a 3x3, I should say, and it goes back and forth by simulation in exactly the same way. Now, it gets interesting when you start looking at multiple excitations, 2 excitations, 3 excitations. And this is an example of something called the Bose-Hubbard model, which traditionally has been implemented in cold atom systems, but we're now able to do it in these superconducting systems. And so we're looking at things like localization, block oscillations in the presence of disorder, which we can fully control and then read out every qubit with superconducting qubits. So these are some things that we're working on now. And we're building a system now that can host up to 64 qubits. Now, initially, we'll probably stick 16 qubit chips in here, so we'll have a few of them, and control those chips using electronics. And this was from a very generous donation from Keysight Technologies. But of course, if we look at this device, we see a problem already, right? And that is these long silvery wires, although they look pretty, they're not very good, and they're called wire bonds, and they take electrical signals from the edge of the chip to the middle, and they're not, from a microwave standpoint, this is a very bad idea. But you see that there's really no other way to do it, because coming in laterally, we've used up all the space already, and clearly if we want to go to 5x5 or 6x6 arrays, this isn't going to work anymore, because we just can't bring the signals in from the side. And so it's clear that we need to 3D integrate these devices, and my group has spent a lot of time working on this over the last few years. And what we've come up with is called a 3-stack. And called a 3-stack because we bump on together 3 chips, like shown here. One is a qubit chip, where the qubits are. One is an interposer, which just basically is an interconnect layer, or sorry, it takes signals from one layer to the other. And then the bottom one is a formal interconnect layer, which has many layers itself, so you can route signals over and under one another with ease. Now, there's a few features here. One is that the qubits, when we do it in this way, the qubits' coherence times are not impacted, because the electric field, for example, from this capacitor sees the same type of silicon chip both above and below it. So even though we flip chip it over, we're not introducing dramatically new decoherence mechanisms. And it's important because this readout and interconnect layer, because of the way we fabricate it to get multiple layers, it actually has some lossy oxides. And so we want to keep the qubits as far away from this as possible. The other reason we do this is that we can fabricate these separately according to their best practice fabrication. Making high coherence qubits requires some very specific fabrication techniques that aren't necessarily compatible with making a multi-layer, fully planarized structure. And so maybe someday we'll learn how to do this all monolithically, but today it's much easier for us to do it separately in 3 chips and then stack them together. So the qubit chip, just a few more pictures. The qubit chip basically is this type of chip without the wire bonds, of course. And then we flip it over onto the interposer. The interposer itself is made from superconducting titanium nitride. It superconducts at around 3.5 Kelvin. And what we see here are long holes that are etched into silicon, about 200 microns thick. And the diameter, it's an oval, but the diameter is 10 to 20 microns. And so the aspect ratio is 10 or 20 to 1. So these are very high aspect ratio, superconducting through silicon vias. And then at the bottom is this multi-layer process. And what you can see here in the light gray is niobium, another type of superconductor, which is layered on top of each other, but separated by dielectric. So each one of these is a wiring layer that is independent of every other one, except where we have vias like this, where we can connect them together. And so if you think of a complicated highway system where you have bridges going over and overpasses and underpasses, that's basically what we can do here. And by bringing the signals in from the edge, we can bring them in until they're right underneath the qubit we want to address with them, and then we bring them up through the interposer. That's how this works. Now, this layer also has Josephson junctions, and that's interesting because there's a form of classical superconducting digital logic called single flux quantum logic, SFQ. And the point is that one could actually think about building some of the control circuitry in this superconducting digital logic. Okay. The other reason Josephson junctions are interesting is that we can make things like parametric amplifiers that can be used to read out the qubits. And so we can integrate them in this layer. We then connect them all together using something called bump bonding or joining using indium, and indium also superconducts. And so last slide is just, I hope I've given you an overview of the many types of engineering and physics that's involved in building a quantum computer, a future quantum computer. And what I want to emphasize is that a new discipline is emerging, which is being called quantum engineering. And what it does, in my opinion, is it bridges the science and the mathematics, the physics, computer science, and math that we need, and we will continue to need in the future. But we also need to bring up to that level the classical engineering disciplines like analog and digital circuit design, control, filters, materials, and fab, and bring them together to build quantum testbeds and ultimately future systems. And so I think quantum engineering is this bridge that connects these multiple disciplines together. And I want to just emphasize, because I sometimes hear it, people saying that, it's just engineering now. In my opinion, absolutely not true. We still have a lot of work to do on the science and engineering and mathematics and computer science, and all of this needs to work together if we're going to successfully build quantum systems. And I think it's going to take nearly every department at our institutions to do it. So with that, let me just finish up and acknowledge my teams, both at the MIT campus in the Engineering Quantum Systems group, also at Lincoln Laboratory, also part of MIT. Basically, this is one team that just lives in 2 locations. And let me also acknowledge our sponsors from the US government. And with that, thank you for your attention and the invitation, and I'd be happy to answer some questions.
All right. Thank you so much, William, for this fantastic talk. So there are a few questions. So I'm going to try and read them out in some order, just some from latest ones, some from the beginning of the talk. So one of the first questions, let's say, this is a slightly more engineering type question. So how would the dielectric loss affect cubic decoherence in 3D integration? What about the package and substrate mode profile? Mustafa is the person who's asking the question. Yeah.
Yeah, so let me go back to a picture that I can reference here. Yeah, maybe this is good. So that's a great question. So 2-level systems, as you know, are basically like catchers in a baseball game, and they're ready to catch the pitcher's pitch, right? And so the qubits have energy, and all of these 2-level systems in the environment are ready to grab it and take it away. And so energy relaxation is the key, I would say, decoherence mechanism caused by these 2-level systems. Now, they can also fluctuate, and if they fluctuate a magnetic field or an electric field, they can cause dephasing, but what we see predominantly is T1 impact by these 2-level fluctuators. Now, in the 3D integration, we thought a lot about this because, of course, if we take a qubit and we put it face to face with lossy dielectrics, then of course that's bad, because basically if this electric field, say from a capacitor, passes into these lossy dielectrics, which is represented by the pink at the bottom here, then it will lose energy very quickly. And that's part of the reason we stick the interposer in between, and we build both the interposer and the qubit chip using intrinsic silicon. So of course it's not perfectly intrinsic, but it's made in such a way that the number of dopants or residual dopants in the material is very low. And by doing that, we basically have a high Q dielectric called silicon, which doesn't decohere these qubits, at least not today. Of course, at some point it will become a dominant loss mechanism, but today it's not. And so by using this interposer in this way, we push away the lossy dielectrics from the qubit. And of course, we know that, just classically thinking, if a qubit wants to give away its energy to a two-level system, there has to be some interaction somehow. And so the electric field must pass through that dielectric, or the magnetic field must pass through that dielectric in some way. And if it doesn't, then it can't give energy up. So basically another way to say it is the coupling would be zero. So by isolating it in this way, we can enhance the coherence times quite a bit. Now, in terms of the mode structure in the qubit chip, that's a great question, and that's going to become an issue as we make the qubit chips larger and larger. And the issue is that the silicon chip is a dielectric, and so it supports a propagating mode. You can think of it as a 3D object, in fact. It has some thickness, right? But if you break it up using these types of vias, then basically you can make the effective size of the chip smaller by breaking it up. And the distance between the vias just has to be much smaller than the wavelength that we're worried about of the microwave. So much closer than, say, a centimeter, 100 microns or less. And by interrupting the chip in this way, we break it up, just as is done with PC boards, right? If you look at microwave printed circuit boards, you'll often find these walls of vias in there, and their purpose is basically to reduce these parasitic modes.
All right, thanks. So the next question is a little bit more on the physics side, I guess. Is there a downside to increasing the number of pi pulses in the Ramsey experiment? I guess the questioner is asking about the dynamical decoupling, if you increase the number of pi pulses.
Yeah, so of course, there's always a trade-off, and as a system engineer, one would have to decide when is the optimal number of pulses, and going further than that would actually harm things more than help. So some of the things that we would think about are, of course, this takes some amount of time to do these pi pulses, and so decoherence is always occurring in the background, particularly T1. So while the pi pulses are correcting for dephasing, T1 is always happening, right? So one could say, I don't necessarily want to just do pi pulses ad infinitum because I'm going to be impacted by T2. Now, the other side of that coin would be that, in a quantum computing algorithm, some qubits may be sitting idle, right? While the algorithmic gates are being applied to other qubits. And in that case, you would just keep applying pi pulses, right? You would just, as long as you have a memory there that's waiting, why not apply more pi pulses, right? At least you can take care of the dephasing component. But where it becomes really a trade-off is that if you're trying to implement a gate sequence and you then choose, or you have a choice, I can insert pi pulses within this gate to try to take care of some dephasing that's occurring in the background, then you would just, basically say, I'm going to keep adding pi pulses until I see that my fidelity gets worse, and then I'll stop doing it. So as long as I'm getting advantage from it, I'll keep adding them. But at some point, I'm making the overall gate so long by adding the pi pulses that although I'm correcting for the dephasing, I'm suffering from the T1 and the overall fidelity goes down. So it's that kind of argument.
But at least I think it's nice that these are pinned qubits, unlike trapped atoms or something like that, where you're also going to heat them and you keep them out of the trap if you use too many pulses. Right? So at least that's something that works for you.
Yeah, that's right. These are definitely fixed and right on the chip. They don't fall off, and we don't need to trap them. Of course, we have other problems. They're not all identical, like natural atoms, and so we have to calibrate them.
Right. So let me get to some other questions. I think this one's somewhat computer sciencey. So just like the question is, just like we have the assembly as an abstraction over binary, do we have a level of abstraction over the qubits? I'm not sure if I follow the question very well, but I don't know if...
Yeah, could you say the first part again? Do we have an abstraction?
The questioner says that just like we have the assembly as an abstraction over binary, do we have a level of abstraction over the qubits?
Yeah, so people are building those abstractions right now, and I think quantum computer science is really starting to stand up as a discipline on its own, where they're addressing questions exactly like this. And so I would say that much like the history of classical electronic computing, where these abstractions have been made continuously, since the earliest days, that these abstractions in quantum computer science are going to continue and advance, both as our understanding of quantum computer science improves, but also as the hardware improves and changes and enables better abstractions to be made.
All right. So I'll combine a few of these questions. So there are questions about what are the sort of interesting and relevant problems that can be solved with a small number of qubits, 10 to 100. That's one end. And then there is also a question about quantum simulation. I'm guessing what's the number of logical qubits needed to solve problems of interest in molecular or solid state physics, for example?
Yeah, so those are questions that are a bit difficult to answer, but let me try. So in terms of today's quantum computers at say 50 to 100 qubits, what really matters is the quality. And quality always matters more than the overall number. And if we had a perfect 100 qubits, then it would be very easy to demonstrate quantum advantage. And in fact, Google was able to demonstrate quantum advantage with 53 qubits, even though those qubits were faulty individually. Now, they were actually quite good compared to superconducting qubits in general, but they still had error rates of say 3 nines. And so again, compared to classical computers, which have 20 or more nines of fidelity, right? So these are still relatively error-prone devices.
Mm-hmm.
But they were able to demonstrate basically using a random number generator, quantum advantage. They could do in 300 seconds with maybe 50 kilowatts of power what would take the world's top one supercomputer called Summit at Oak Ridge National Laboratory in the US. It would have taken that computer at least a few days and tens of megawatts of power, right? And 10 to the 17 transistors, right? Versus 53 qubits, right? So this is clearly a demonstration of quantum advantage. But then, of course, you could say, and so I like to think of that as the Wright Flyer got off the ground and it flew a few hundred feet. But then you could say, what can I actually do practically with that? And aside from generating random numbers, it's not clear yet at these small size scales. And so there is a lot of research going into what's called NISQ, noisy intermediate scale quantum algorithm development, which basically is asking the question, given these noisy qubits I have today, if I had 100 or maybe 1,000 of them, what could I do? Is there something I could do, and is it commercializable? And we don't know the answer to that yet, to be honest. People are thinking very hard about it. And I think one of the promising directions, or at least hopes, is that if you run the quantum computer as a co-processor with the classical computer is doing most of the work, but then it gets to a part of the problem where it wants to poll the quantum computer for a quick answer. And the quantum computer can do that within the lifetime that it has. And these would be problems related likely to optimization or variational quantum eigensolvers. But to my knowledge, as of yet, we haven't identified the smoking gun application which is going to lead to a commercial application that we care about. And it's in part because the number of qubits is small, but it's also because the quality of those qubits is not quite high enough yet. Again, if you had 100 perfect qubits, that would be great. But that's not what we have today.
Yes, and so there was an earlier question from another listener. So they had a question regarding applications in high energy physics with qubits, and I wanted to sort of join it up a little bit with the last stuff that you showed with these 12 array qubits. Have you also thought about building these plaquette type interactions? There were these proposals, I think, some from Innsbruck, where you could actually make a sort of a 4-particle interaction, sort of 4-qubit interaction. So these things are really cool. If you could do it, you could actually simulate some gauge theories, for example.
Yeah, so let me answer the last one first. So I do have a student who's working on 4-body interactions. in the context of quantum annealing, related to that paper I think you're talking about. And so we've been able to do it. And now the question is, can we do it with higher fidelity? So I think that it's going to work where we have a true four-body interaction, not some approximation to it, but a true four-body interaction. But it will work for quantum annealing where the premium on coherence is not as high, but I don't think it's ready yet for gate model. It's not at the 99.9% level yet. It's much lower than that. So, but it's the first time we've tried it. So I think that, we'll learn and do better. But anyways, the student is, sort of taking final measurements on that. And I hope we'll publish something within the next few months related to the four-body interaction.
Okay.
And in terms of high energy physics, I think there's certainly simulations that could be done or constructed. And I think it's an interesting direction to ask how quantum computers could be used to solve problems of interest to the high energy physics community. But I would also say that another way that these two fields can work together is through detectors and quantum sensing, and trying to apply quantum technologies to the implementation of high energy physics experiments. That's also, I think, to me anyways, an interesting direction.
Okay, fantastic. So I think we have a couple of more questions, but I think we've sort of been around more than an hour, and I think it's sort of a good point to stop. But I would stop with one question that also came in from someone, and if you thought the other ones were harder to answer, this question is somewhat more ambitious. So when do you expect the number of logical qubits to reach 1 million or more?
I hope it happens in my lifetime.
Yes, very good. On that note, I think I hope so too. And thanks a lot to all your questions from the people who are listening in. Thanks a lot, William, for this fantastic talk and your time. And hopefully we'll get to see you in IIT Gandhinagar in person at some point, and also before that, hopefully in a physics colloquium as well. All right, so that's it from me. So Sanjay, you can take over and conclude the session.
Again, firstly, thank you so much, Professor William, for spending so much time. And it's been a very insightful session. I'm just a second year undergrad, but I still have had some takeaways from the session, and I'm really enthusiastic about the future that quantum engineering has for us. So I would like to, I really appreciate your time. And on behalf of the entire Amalthea team, again, we thank you for your time, and we hope to see you at our campus sometime soon, and hope to interact with you in person as well. I would also like to thank Professor Prasanna for spending his time for hosting the session. And thank you for all the participants for staying till the end.
Yeah, and let me also thank you again for the invitation. I really enjoyed it, and I'm also looking forward to a time when we can all travel and get together again. So thank you very much.
Thank you, sir. I think we can wrap up the session.
Okay. Goodbye. Thanks.
Thank you, sir.